Look at this perfectly straight, frictionless horizontal track. It is designed for precision physics experiments, eliminating outside variables to isolate a single linear path. On this track, we have two objects. Block 1 is the striker, and Block 2 is the stationary target. The simplest collision is a head-on one, straight line in, straight line out, but with powerful equations underneath. We call this a one-dimensional collision because the velocity vectors of both objects lie exactly on the same coordinate axes. This diagram shows our striker on the left with a mass of m1 and an initial velocity v1I moving toward the right. Waiting in its path is the target, mass m2. Its initial velocity is 0. It is perfectly at rest. In this scenario, the initial state is entirely measurable. We know exactly what is about to happen, but the state of the blocks immediately following the impact is a complete mystery. To solve that mystery, we need to find the post-impact velocities, v1f for the final speed of the striker and v2f for the target. While the physical crash happens in a fraction of a second, it represents a strict transition between two different states of energy and motion. To predict exactly where these blocks end up, we have to look at the hidden mathematical laws governing every impact in the universe. The first rule we rely on is the conservation of linear momentum. This dictates that the total momentum of a closed system before a crash must exactly equal the total momentum after. Momentum, represented by the lowercase letter p, is simply the product of an object's mass and its velocity. Let's examine a completely inelastic collision. Here, the two objects strike each other and instantly fuse into a single moving mass. This happens because the initial kinetic energy is spent on permanent deformation, locking the objects together. This equation shows the momentum balance for that inelastic crash. Because the blocks move together, there is only one final velocity, Vf. We add mass 1 and mass 2 together in the parentheses on the right side. By rearranging the equation to isolate Vf, we get equation 5.22. The final velocity is the mass of the striker divided by the total mass multiplied by the initial speed. In this fused state, the momentum is preserved, but a significant portion of the initial kinetic energy is lost to heat and deformation. This sticky crash serves as a baseline. It establishes the simplest outcome, allowing us to analyze the more complex dynamics of objects that bounce. Now we leave the sticky crash behind and look at the perfect bounce, the elastic collision. In a perfectly elastic impact, the objects behave like ideal springs. They compress upon impact, but instantly snap back to their original shape without losing any energy to deformation. This introduces the second rule, the conservation of kinetic energy. Kinetic energy, denoted by the letter K, is the energy of motion. It is calculated as 1/2 an object's mass times its velocity squared. Because the objects snap back perfectly in an elastic collision, the total kinetic energy of the system immediately before the impact must be identical to the total kinetic energy immediately after. We still have two unknown variables to find, v1f and v2f. Fortunately, we now have two independent mathematical rules to find them. This diagram shows our two rules locked together, equation 5.23 representing momentum and equation 5.24 representing kinetic energy. These two laws acting simultaneously create a strict mathematical filter, leaving only one unique, predictable solution for every head-on elastic collision. Solving for two unknowns simultaneously requires algebraic manipulation. We have to filter out one variable at a time. We rearrange the momentum equation, moving all mass 1 terms to the left side. We do the exact same for the kinetic energy equation, discarding the common 1/2 fractions. Next, we expand the difference of squares on the left side into two separate parenthetical terms. Now we divide our expanded energy equation directly by our rearranged momentum equation. This triggers a massive cancellation. The mass terms vanish entirely, along with the v1i minus v1f term on the left side. What remains is equation 5.25. The initial and final velocities of the striker added together equal the final velocity of the target. This simple relationship strips the mass variables away completely. Relating the velocities directly provides the missing link for our final equations. We substitute this new definition of V2F back into our original momentum equation to isolate V1F. This gives us equation 5.26, the final formula for the striking block's exit velocity. By substituting back the other way, we reveal equation 5.27, the formula for the target block. We reduced the conservation laws into two specific formulas that calculate the final speed of each block based solely on their initial mass and velocity. We can test these formulas against real-world extremes. First, consider two objects of identical mass, like billiard balls. In the formula for the striking ball, is mass 1 equals mass 2, the numerator, mass 1 minus mass 2, becomes exactly 0. The physical result is stark. The first ball comes to a complete stop. In the formula for the target ball, plugging in equal masses turns the fraction into 2m divided by 2m, simplifying precisely to 1. The second ball inherits exactly 100% of the speed and direction of the first ball. When masses are equal, nature performs a perfect handoff, transferring all kinetic energy and momentum seamlessly from one object to the next. Now consider the opposite extreme, a tiny striking mass hitting a massive target. If mass 2 is much larger than mass 1, the term mass 1 minus mass 2 effectively becomes negative mass 2. Divided by a denominator of mass 2, the entire fraction approaches negative 1. The math perfectly maps to reality. The light object bounces backward at its original speed, while the heavy target remains effectively stationary. These extreme behaviors are not random. They are the strict, inevitable outcomes demanded by the algebra of conservation. One-dimensional collisions are the cleanest training ground for understanding momentum and energy conservation together. By mastering these rules for one-dimensional motion, we establish the foundational framework needed to analyze more complex, multidimensional interactions.